Hey everybody, welcome back. So today what we're going to do is we're going to pick up some, I wouldn't call it advanced topics, but it's more material that we can use to look at the outside world and how structures behave in the context of statics. All materials, as we've dealt with so far, are created equal. They're all just material X. Whereas real world materials are made of different things. They have different capacities to carry load. And in the next couple sessions that we're going to talk about failure. And one of the primary jobs of an engineer is to design to build things that do not fail. Because usually when things fail, people get hurt, and that's effectively our number one job is to be safe in things that we design. So as we switch our thinking more into designing things, we need to have this discussion about, well, how do things fail? So the first thing we're going to learn about with respect to failure is the notion of stress. And just like people, materials do not like to be under stress. And too much stress, they break. So let's talk about what does that mean. In the context of things that we've learned about already, we know that, especially with trusses, all trusses are made of two force members. And so for two force members, there are two configurations you can have. You can have tension or you can have compression. So these are the two force states that we can get for any particular member in a truss. So these are forces. So F minus F. And they only differ by the direction. Okay. What is stress? In the context of what we're talking about now, let's say we sliced open. If we could take a magic knife or something and cut right through the cross section and look, and we drew a free body diagram or looked at what was going on in there, what we'd see is we would see this surface that we just exposed. Okay, we're not applying, let's say down here, here's our force that we're applying, we're pulling it. This section has to be in static equilibrium, right? The forces have to balance out. But there's no applied force here in the interface. And this is where we get this notion of stress. So you can think of stress as a bunch of tiny little vectors which are coming out of or perpendicular to that surface. These are our little stress vectors. The simplest way to express this is to say stress, the Greek symbol sigma, in tension, in uniaxial tension or compression, it turns out. But when you have this particular loading configuration, the stress is just the ratio of force divided by the cross-sectional area. So, I drew it as a round member. We know that A would be pi r squared, just the area of that projected circle. So if we knew that A, we could plug that into there. And if we knew how hard or soft we were pulling or pushing on an object, we could calculate this stress. So just like you have, this would be tensile load, and this would be compressive load, you'll have tensile stress and compressive stress. Okay, so this is the formula. I mean, this is as deep as we are going to get into the notion of mechanics of materials or how stresses evolve inside parts or structures. There are many different types of stress, and you can spend a whole graduate career learning nothing about stress. But as far as we're concerned and where we're going to go, this is sufficient. So uniaxial, one axis, tension or compression, this is the expression for stress. If we looked at that equation, F over A, and just in terms of units, we have force over area. So unit of force would be a Newton in SI units. In area, typically meters squared, but I'm going to use millimeters squared, and you'll see why. All right, so, well, a Newton meter squared, this is defined as a Pascal. Okay, this is a derived unit. Pascal is Newton per meter squared. I like to express it in newtons per millimeter squared. This is a little trick that you pick up over the years. Is a Newton per millimeter squared is 1 megapascal. Right, megapascal. 1 million pascals is a Newton over 1 square millimeter. Trust me, you're going to like this later on. All right, so what's interesting is stress and pressure share the same units. It's kind of interesting. If you want to do the U.S. customary units, you have unit of force is pounds over inch squared. That gives you 1 psi. All right. So what you'll see is more often these are thousands of psi or ksi, so thousands of psi. But anyway, these are the characteristic units that we're dealing with: force per unit area, force per unit area. All right, so how does this relate to materials? Well, real-world structures are made of different things, and different materials have a different capacity for stress. So what I would say here is, since real-world materials have physical limits, let's look at those. So I'll make a little chart right here, and this is not exhaustive, but this is just what I pull off the top of my head. Aluminum, very common material because it's very light, it's fairly strong for its weight, and relatively inexpensive. And let's look at steel. Probably one of the most common structural materials in every large building, concrete and steel. It's the building material of the 20th century. All right, so if we look at these two, you look it up in, a lot of these are just tabulated. You don't have to discover these on your own. Many people have done a lot of work. There is this special stress called the yield stress. Right? And this is known for most materials. The yield stress is where the material yields. And without getting too far into it, when you yield a material, you incur permanent damage to that material. So think of a spring, all right? So as you compress or stretch your spring, it goes back to where it was. All right? So that's an elastic behavior of the material. There's no permanent damage. But if you pull hard enough or stretch hard enough, that spring doesn't go back to where it was. You've incurred permanent damage. You've effectively yielded that spring. I can go over here and show you a quick demo on the document camera. And while it's warming up, what we're going to see is I'm going to incur permanent damage to a material that probably most people have access to, which is a paper clip. All right, so we have this paper clip here. Very easy to yield. I mean, if I do it gently, you could do this yourself. You can feel it springy, and it's back to the way it was. But then if I just keep applying more and more and more load, I can incur permanent deformation, right? I have yielded this material, and it's probably some weak steel, even aluminum paper clip here, right? So hopefully you can see. I mean, you can do this at home. You can bend it. It's kind of springy, and then you just keep bending it. I'm yielding. You keep going. It's actually a pretty robust paper clip, but eventually you'll break the paper clip. All right, we can come back to me. So that's where there's a stress level. In uniaxial, I wasn't doing uniaxial stressing. I was bending it. That's a different flavor of bending or of stress. But uniaxial stress, there are limits to materials. So for aluminum, you look it up. You will go, and you can probably find different values. But for aluminum, ballpark 90 megapascals. All right. So this is why I like this little shortcut here. Is most stresses for materials are quoted in megapascals. Sometimes gigapascals, but usually megapascals. So 90 MPa, 90 megapascals for aluminum. Depending upon, there's myriad different flavors of steel. But you can look at here, let's call it 250 megapascals. So you can see, if you didn't know anything about metals or metallurgy, most people generally know that steel is stronger than aluminum. Well, here you can see why. It has a larger capacity to carry load per unit area. It's, almost 3 times as much. So this is the yield stress. So if you look at this equation here, the yield stress would go into here. You have the relationship between the force applied to whatever you were applying it to in the area, the cross-sectional area. So that's the yield stress. What are some other material properties that we're going to deal with? Well, there is when I was talking about springiness, All right, I'm going to do a large generalization here, but springiness, elastic modulus it's called. It has this symbol E. You can think about, the spring constant of something, then it's related to its elastic modulus. This, for aluminum, would be 70 gigapascals, so 3 orders of magnitude larger than that, but still the same, interesting, same units, right? We have steel. What is the modulus for steel? Elastic modulus for steel is 200 gigapascals. We're going to see, we'll definitely pick this up next section, how this becomes very important. But for now, we're just looking at differences in materials. Now, what I would say is density. So density, in kilograms per meter cubed, right? The amount of mass per volume. Well, if you just had an aluminum bar and a steel bar, you'd hold them. You could tell which one was the steel bar because it's a lot heavier per unit volume. Right? So the density difference is, for aluminum, it's about, I'll just call it 2,700 kilograms per meter cubed, and for steel, 7,850. So a substantial density difference that we perceive as weight given the same amount of volume. So as we can see here, choosing between aluminum and steel depends on what are you after. I mean, do you want high yields? You want high yield strength? Do you want low weight? We'll see how modulus plays in next time. So as a designer, these are the things you have to take into consideration when you're choosing materials. What else is there? Well, actually, I left probably the most glaring one is cost. Sort of cost in US dollars. I looked that up in preparation for this lecture. I think this ends up being about $2. I'll do this dollar per kilogram. That was how it was quoted. So US dollar per kilogram. This was 2, and this was 1. That's what I found. Perhaps I'm right, perhaps I'm wrong, but my cursory search developed this. So this says, for the particular steel that I was looking at, particular aluminum, you might get a better deal if you look around. But you can see here, weight is a factor, perhaps cost is a factor, yield stress is a factor. All of these materials considerations come into play when you're designing a structure to undergo load that, in the absence of that, you would just make some design and assume all materials would behave the same, and they don't. Okay, so with that, I think I'm going to conclude this particular section, and the next section, what we'll do is we're going to learn about a different failure mode where this particular failure mode yield is only tension. So there are people whose sole job is to sit there and take materials and pull them apart until they yield, until they incur permanent damage in the sample. And that's basically how all these tables are performed, right? So remember that. What I have here, this yield stress, this is the tensile yield stress. Next time, we're going to pick up what happens when you have compressive failure, which is a little bit different, all right? So see you next time.